Hi, my name is Skylar Moe, and today I will be presenting Lab 2 in Physics 2211, and we will be discussing motion of a falling object. So our major concepts here are Newton's second law with a net force not equal to zero. This can be written as final velocity equals initial velocity plus F net over m times delta t. An object that falls to the ground has a non-constant velocity, and this indicates that F net is not equal to zero. So we must explore what forces are acting on the object. Well, we have the force of gravity, or the weight force, which is the force between any two objects with mass. We calculate this on Earth by multiplying the gravitational constant, or 9.8, by the object's mass. And then we have the drag force, which is described as a force opposite to any object in motion. We calculate this by using the equation b times velocity squared, where b is representative of a proportionality constant dependent on the airflow around the object. We will also begin to explore terminal velocity, which is the point where an object in free fall gravitational force is equal to the force of drag. So in this video, I analyzed a scrunchie and tracker. As you can see, I set my axes where the origin is at the center of the scrunchie. As we watch the tracker video, as I drop the scrunchie, the spaces between the red dots becomes larger and larger as the scrunchie accelerates closer to the Earth. As we look at the chart on the right, we see the position of the cup versus time as the scrunchie falls to the ground. So then we jump into glow script code. On line 49, G is equal to 9.8, which is our gravitational constant on Earth. Then on line 65, we have our time parameters, which I derived from my tracker video and tracker data. And then on lines 70 and 71, we have our Fnet statement, where we set the weight force equal to negative ball m times our constant g times the unit vector j hat. Then we set our Fnet equal to w. Also, on line 75, we have to use the velocity update formula, which is also known as Newton's second law. So right here, we have our glow script model that I'm going to run, and we see that our computational model follows around the same path as our experimental model. And so here we just compare our experimental and computational data with just gravitational force. We can see our experimental model had a slight higher position than the computational model. The computational model seems to have dropped faster than the experimental model. This might have happened because we did not take into account the drag force in the computational model. So now we go back into GlowScript and adjust for drag force. On line 71, I set the force of drag equal to negative b times the magnitude of the ball's velocity squared times the negative unit vector j hat. And then for our net force, we add the weight force and the drag force. We keep the velocity update formula the same because that is a fundamental concept of physics. When I run this simulation, the force of drag is upward and the force of gravity is downwards. As the ball's velocity increases, the drag force increases due to the direct relationship between the drag force and velocity. So here I plot all three against each other, and we can see that the red line is the experimental data, the yellow line is the computational data taking into account drag force, and the blue line is the computational data only taking into account the gravitational force. We can see that when we added in drag force to our glow script code, it revealed a much more accurate model reflecting the real world. We then want to examine the velocity versus time predicted by our models with and without drag. Which models, if any, predict terminal velocity? Terminal velocity is the constant speed that a free-falling object eventually reaches when the resistance of the medium through which it is falling prevents further acceleration. The model without drag force exhibits constant velocity, while the model with drag force will exhibit terminal velocity given the right amount of time. So the next step was to see if an object was thrown down with an initial velocity, would the terminal velocity be the same or different than when the same object was initially dropped from rest. In this case, the terminal velocity would be the same because the terminal velocity is not dependent on initial velocity. Instead, terminal velocity is the point where the force of drag equals the force of gravity, and therefore acceleration is equal to zero. The object that was initially thrown downward will reach terminal velocity faster and will travel farther, but both will achieve terminal velocity.